In this video, we're going to talk about a specific problem called a regression problem, and we'll be focusing on linear regression. First, let's understand what a regression problem is. So regression problem pops up whenever we want to predict some numerical values here. Let's first understand the terminologies that is used in our video. So first of all, we will always have a data set which will also be called a training set. So each row in this data set will refer to one example in the training set. It'll also be called a data point or an instance or a sample of our data set. The things that we're trying to predict will be called as a label or a target, and the variable that will be used for prediction will be called a feature here. So taking an example, we see a small housing price data sets here where we have area, age and the price. So basically price is the thing that we want to predict, so we'll call this a label or a target. We have three rows of data here, and the entire collection of these three rows will be called a data set. Each row will refer to one sample in a dataset or one example in a dataset. Before moving on to the regression problem solution, we'll try to establish a few assumptions here. The first assumption is that the relationship between the feature x and the target y is linear. That is, the expected value of y given x can be expressed as weighted sum of feature x. This setup will allow that the target value may still deviate from its expected value on account of observation noise. And the second assumption is that any such noise is well behaved and it follows a Gaussian distribution. We'll also consider a variable n, which we will use to refer to number of training examples in a dataset. Now let's move on to the model. So at the heart of every solution is a model that describes how features can be transformed into an estimate of the target. Assumptions of linearity means the expected value of the target can be expressed as a weighted sum of feature. Example, if we want to predict the price, this particular price can be defined as a weighted sum of area, where we have a weight value for area and the area value itself, and then the weighted sum of age, where we have weight value for age and then the age value itself, and a bias where W area and W age are weights and B is a bias. What weights do is weights determine the influence of each feature on our prediction, and bias determines the value of estimate when all the features are 0. We can also call this equation as a transformation of input features, which is characterized by a linear transformation of features via a weighted sum combined with a translation via the added bias. So given a data set, our goal is to choose the weights and bias in such a way that it makes our model prediction fit the true prices observed in the dataset as closely as possible. So when our input consists of D features, we can write our target as y hat equals to w1 x1 plus w2 x2 plus and wdxd plus bias. In terms of our example, where we have only two features, area and age, so x1 becomes area and x2 becomes age. So our regression equation can be written as y hat equals to w1 x1 plus w2 x2 plus b, where x1 is the area and x2 is the age. So collecting all the features into a vector x and all the weights into a vector w, we can express our model compactly via the dot product between w and x here using this particular equation. In the third equation, the vector x corresponds to the feature of a single example. We find it convenient to refer to the features of our entire dataset of n examples. So we'll represent our entire dataset x as a real valued matrix of shape n into d, and then for a collection of features x, the prediction can be denoted as a matrix vector product using y hat equals to matrix X into vector W plus B. If you see equation number 4, we see that this is equivalent to a equation of a straight line y equals to mx plus c. So our optimal goal is to fit a straight line in between our training examples in such a way that all of these points or all of these data points or data samples that are present in the data set fit very closely to the fitted line here. But we see that we don't always achieve that. There are some minor errors that we need to talk about. So let's talk about the loss function. The most common loss that we use in case of the regression problem is a squared error. Suppose when our prediction, for example, I is y hat I and corresponding actual value is yi, then we represent our squared error as loss for weights and biases equals to 1/2 times y hat I minus yi whole squared. So if we look at this equation, we note that a large difference between estimates in y hat I and yi lead to even larger contribution to loss due to its quadratic nature. So to measure the quality of model on entire dataset of n examples, we simply average the losses of the training set and then we can represent it in this way as done in equation 6. So what we're doing here is we're basically summing up all of the losses of each training example that we have and then we're averaging the value of loss here. When training the model, our main goal is to seek the parameters W and B in such a way that it minimizes the total loss across all the training examples, and this is the objective of our regression function. Luckily, linear regression is a special problem where we also get an analytical solution. If X is our matrix representing our input features and Y is our vector representing our output feature or the labels or the target, then the optimal value of weights can be computed using equation 8 here. But this is not always the case in terms of a machine learning problem. Fortunately, even in cases where we cannot solve the models analytically, we can still often train the model effectively in practice. So the key technique for optimizing nearly every deep learning model consists of iteratively reducing the error or loss by updating the parameters in the direction that incrementally lowers the loss function. And this particular algorithm is called gradient descent. The most naive example of gradient descent is to take derivative of the loss function, which is an average of the losses computed on every single example in a dataset, or where we consider the entire dataset at once and then we update our steps. But in practice this can be extremely slow. Well, there is also another alternative. We can only take one single example and then update our step based on every single examples, but again this is also not convenient. So what we do is we take an intermediate solution here. What we do is, instead of considering the entire data set or just one example, we consider a batch. We consider a mini batch of our data set, and then rather than taking the complete data set, we take a mini batch of observations, which is called a stochastic mini batch gradient descent. So the algorithm for this is, we first initialize our weights and biases randomly, then we fix a mini batch size, let's represent this as beta, and then we fix a learning rate, which will be non-learnable parameter in our model. Then we take a mini batch from our dataset based on the mini batch size, and then we compute the loss against the previous weights and bias. We take the derivative of the loss or compute the gradient. We take the small steps based on the learning rate and then compute the updated weights and bias in this way. So the updated weights and bias is going to be the previous weights and bias minus the learning rate, the normalized version of a mini batch, times the partial derivative of our loss function. And then we repeat this step until we get such value of weights and bias which will minimize, or until we get the most minimum value of the loss for our dataset. Using this approach, mind that we might not get the exact solution as provided by the analytical solution, but we'll get somewhere close to it, and we'll also consider it as a good solution until and unless there are more low values that can be attained using this approach. So this is all about linear regression, or the regression problem as a whole. I'll also upload the code implementation of this particular approach in the upcoming video. So stay tuned.